Japan is so
Yeah,
good.
exactly. So I feel like after we just after this some exercise. Otherwise,
And you'll be able to.
I can introduce him, yeah.
Oh.
Are there people who are connected? Yeah, there are. I think Joe was the coordinator for this one, but I'm not able to come first. He might connect later. Begins to feel like we're about to learn some secret knowledge about pions. Yeah, you never know if there's a drone.
oh, no, that one's
No,
fine.
I think that was a joke.
That was a jet.
Yeah. The Russians inside of it. Well, actually, we're all.
That's part of it.
Already, we're into my clock, but not about, we're 2 minutes past the official state of party. I think some folks might be traveling, so maybe we should sort of dive in, and then maybe some people will come in as we go. So it's really my delight to introduce Leonardo Rastelli today. Leonardo was a faculty member at Princeton for a few years before taking up his position at the Young Institute for Theoretical Physics, Stony Brook. He's the director of the Simon's collaboration in non-perturbative bootstrap. And in fact, today he'll tell us about the bootstrap and its application to a theory we all know and love, which is QCD, in particular, large unlimited. So
Thank you very much. It's a pleasure being here. It's a wonderful day. So yes, I will talk about some work that we did and we're still doing. It's sort of at the beginning of what I consider a sort of long-term research program with my wonderful fellow student John Albert, and I get to it some work in front with people as well. The idea is an old one. In fact, so old that so one of the very first questions we need to answer is, okay, what do you think you can add to the story that wasn't already done in 1965 or perhaps a little later? And the idea is to, really going back to the original incarnation of the bootstrap program, the bootstrap for estimating sort of strong interactions, where people were despairing of, every week a new resonance was discovered, or were despairing of any sort of discovery understanding, and so there was the idea of nuclear democracy. We should read all these funny states on the same footing and try to bootstrap our way through the general asymmetrics using only very general. That program, of course, as we all know, sort of failed, but not completely failed in a very interesting way, giving rise to the seeds of string theory by duality with the Mesons, and that whole story that we're familiar with. And then, of course, QCD is the correct theory of the sonic. Why bother going back to that story? And of course, the answer is that QCD is very hard to solve. And although this is an old story, we also have in some ways got wiser. And one philosophical theme of recent progress has been that perhaps our forefathers had all the correct ideas, but perhaps were a little bit too ambitious. They were trying to get inspired. And one bright morning, wake up and write down the exact answer as a ratio of gamma functions. That was too ambitious. And so we should retreat a bit and put the problem into a broader context. So rather than trying to solve once and for all a simple theory, we can use this more modern viewpoint of looking at theory space. And what is the relevant space of theory that we will consider today is the space of large N. Well, we concrete, let's do it. Because one dimension we consider the space of large N confining H here, which of course QCD is the one that we ultimately like to zero in. But the point is that really it's useful to consider this whole family of theories. And there's a key simplification in the Bootstrap program for the S matrix that happens at large N, which is that we really have an infinite power of stable hadrons. And their S matrix, since they are really stable particles, they give rise to poles as opposed to cuts. In the S matrix, so the analytic structure is much simpler. And just as a little warm-up, I will explain this in more detail later. Consider, for example, 2-to-2 scattering of say the lightest particle in the theory, which for us would be the pions. And or more generally, consider the set of all hadrons and consider the all possible 2-to-2 S matrices. And it's sort of clear that this the data that you need in the first approximation, we can be a little bit more precise. In the first approximation data you need to write down this infinite set of S matrices are the on-shell data, so the masses and the spins, as well as the 3-point on-shell couplings. But it's also clear that not anything goes. So this set of data has to satisfy a variety of constraints, such as unitarity and crossing. And the crossing equation here is the good old statement of duality. There's the statement that, so here for simplicity, I'm looking at the case of identical massless particles, we know the channel poles, which will be what will be important for us in a bit, as I will explain in more detail, but just as a first indication, the type of consent that we have, the idea that everything is meromorphic, and under certain assumptions about the high energy behavior, you can actually prove that the ampere must have two equivalent but differently looking expansions, one where you sum over the S channel poles, and the other one where you sum over the U channel poles. In my conventions, Mandelstam S will be the usual center of mass kind of variable, and Mandelstam U will be momentum transfer. In the literature, perhaps sometimes U is in place with P, but that's just
So the P functions are the analytic. There's no
right.
P function there is
And the
analytic.
P function is that not always analytic, but it's a well-known function, just a Legendre polynomial. This is just the kinematics of the rotation. So this is a Legendre polynomial that just take into account that there is changing a particle spin J. Okay, so that's of course the whole idea of duality. You must get this meromorphic amplitude either by summing over one set of poles or in the cross channel. You don't have to. If you were to sum over both, you'll be overcounting. And in fact, under suitable analytic assumption that I will review in a minute, this is a theorem. It just follows from writing down from Cauchy theorem in the complex.
What is the relation between the lambda n in the expression there and the lambda ijk?
So the lambda ends here. So this I'm fixing at the external states. So these are two. So this would be if the first states is state number one. Say this would be lambda 1 where n runs over all the possible states that be. So
I understand.
So I'm doing. This is an exchange where I'm fixing 1 and I'm summing over n. And so here I do that.
But which amplitude is under consideration, Leonardo? It is pi scattering?
Excuse me?
I wonder what the amplitude of the 2. It is a pion scattering or something else?
This is really an appetizer. I will come back to more details later. This is just an equation I wrote down to give a sense of the fact that there are constraints, and this is one such constraint. Obviously, not an arbitrary set of masses and counters will not obey such equation.
No. I just wondered because, for example, if it's a pion scattering, then there is no pole at m pi square NS, right?
So- So
Because
this,
S minus m pi square.
I will give more details later. This, you can think of this as the scattering of massless pions. And there's definitely no poles, there's no intermediate pion scattering poles for a variety of reasons, including quantum numbers. So the lightest resonance exchange with the rho. But I'll come back to this.
No, yeah, but I still did not get. It is two amplitude. It is a scattering of which particle? Let's say that we are talking about pions. Then it's not pi scattering, right? You are talking about.
I will actually be talking about pi scattering.
For pi scattering, there is no pole at S equal m pi square.
But where do you see m pi square here? Sorry.
It is lambda divided by S minus m pi square.
Oh, that's MN.
N, this is N. This is Mn. N is an integer. M1, M2, M3, this is the complete set of mesons which are scattered in pi.
But did it spin 1 or spin 0?
Sorry, this is a schematic equation. That's supposed to ask any question. It's a schematic equation that will be explained in more detail later. However, it's also a correct equation.
So it's not m pi square because
There's no pi. I don't know where you see pi. This is N.
Here I see pi where
I
it's
see them
lambda
above.
n squared divided by S minus what?
N.
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 I see. I got it because to me it looked like pi. That's why I asked.
No. There is a sum over the infinite. This is
Sum over all pies.
I see.
Intermediate points.
I see. Okay, I got it. I'm sorry.
No. Okay, so this was just a way to start with this broad framework. And sort of, if you squint your eyes, this is clearly very similar in spirit to the conformal boost. Okay, so in the story of the conformal boost, those of you are familiar with it, the data that specify the conformal will be anomalous dimensions and spins and OP, the cubic OP couplings. And famously, not anything goes, and the constraints of unitarity and crossing, for example, lead to this beautiful exclusion plot where under extremely general assumptions, for instance, the fact that we are in 2 dimensions, the fact that there's a single relevant scalar, which is Z2 odd, and a single relevant scalar, which is 2 even, we find that there is a exclusion plot. What's inside the blue region here is allowed, what's outside is disallowed. And serendipitously, it happened that the 3 Ising model precisely sits at this kink. So what we would like to do is to draw a similar plot here, a similar exclusion plot in the data that specify a large N confining H theories in the hope, which at this stage is really just a hope, that perhaps QCD will sit at some spectral point of this exclusion plot. And so the principle we use are the good old principles of the S-matrix bootstrap, but now from this more general point of just carving out theory space. Okay, so I will explain all this in detail, crossing similarity with parities and certain requirements about that. And so now, of course, the theory that we would really like to say something about is large N QCD. So, of course, this is just Young-Will's theory in the top limit of fixed lambda QCD. For definiteness, I will mostly take the number of light quarks to be 2, but as it will become clear in a minute, there's some trigger group theory you can do to generalize from an F to general NF. The flavor structure will completely further out. So famously, this is of course the theory of glubots, mesons, and baryons. In the large and limit, the baryons are heavy. And you might think that the conceptually simplest thing to do is to start with the glubots. There are, however, a couple of good reasons to focus on the mesons. One is that, of course, we have a lot more guidance from SPERG. We really do know this meson spectroscopy very well. Global spectroscopy is something we can try to solve from the lattice, but it's hard. And second is that there are the kinematics of meson scattering are a little bit more constrained for a reason that that I will review. Having to do with the fact that for example, a large N, the spike rule becomes exact, and that imposes a very interesting kinematic constraints on the structure of the S matrix. And so what we will be interested in is again pion scattering, which you can organize in the usual Toft expansion. The leading diagram is one where the leading set of diagrams is one where we have an external quark loop. That's goes like N, and then of course you can insert either internal quark lines or non-planar geometries. And there is an obvious analogy with the topological expansion of a string theory. That's of course one of the holy grails on the subject, precisely characterize the work theory that corresponds to large N QCD. For us, this will just be a sort of underlying motivation in the back of our mind, but we will not make any such manifolds. And so we will again. So we work. Our target, but again, our assumption will be sufficiently general. There will be many theories that try to fit this assumption, but our eventual target would be QCD with an F massless quarks in the large N limit, and then we will assume the usual partner of chiral symmetry breaking, which is a very safe assumption that there are theorems that extend for large N, that this is the partner of chiral symmetry breaking, and so we will have the usual massless pions. In fact, at strictly infinite N, the U1 axial anomaly is suppressed, and so famously, for example, in the case of three quarks, the eta prime is also exactly massless as large N, and so you really have a non-net rather than an octet. But as you will see, the kinematics will work in a very uniform way.
But the amplitude of pi scattering has a it's a finite limit of large N, or it is proportional to N.
So the way I normalize it will be finite. Well, let me.
Mm-hmm.
If you normalize the if you normalize the wave function to one, to absolutely leading order in N, the leading diagram is just factorized. It's just free scattering, right? So
okay.
In the large N limit, everything is free, right? Mm-hmm. So if you correctly normalize the amplitude, the pion scattering we actually go like 1/n, will be infinitesimal. So the coupling constant is 1/n, or 1/√ square root n for the three mesons. So let's review a little bit of kinematics. So famously, we can take into account the flavors. So again, in the case of SU2, for simplicity, we take into account the flavor structure by polymatrices for the Champaton flavor degrees of freedom. And so at the end of the day, the entire connected amplitude leading order in N is captured by a function of two Mandelstam variables. Again, this is of course reminiscent of the construction we do in string theory, where this diagram, but I want to emphasize that this is literally just following from large N count. We have a quark line in the external leg, and A, B, C, D are adjoint indices of the flavor group. And the key simplification happens at large N is that everything is really stable, and so we don't have any cuts. We have a sum over infinitely sharp poles. The first one will be the rho, then there's the F2 meson, etc. And the other important simplification, which is sort of obvious from this planar, the way we write the amplitude as a planar diagram with an external quark loop, is that the amplitude really only has two degeneration limits. In this diagram, where A goes to B or where A goes to D. So there are no mesons which are exchanged as A goes to C. And you can rephrase that in the old language of meson phenomenology by saying that a large N, there are no exotics, so mesons are exact Q-bar pairs, and that being the case, although a priori pi scattering would contain isospin 0, isospin 1, and isospin 2, the isospin channel is actually exactly absent in the language of large N counting. That's a subleading diagram.
What about spin 0, sigma resonance?
Okay, the sigma resonance is a tetrapore. So the sigma resonance in this language is not a QQ bar state. It's a broad resonance which should really be understood as a double trace state.
I see.
So it's not a single pole in this you would see that in a multi-particle process where you have tetrapoles. So the absence of the isospin 2 channel, if you think a little bit about it, is the statement that that there should be no T-channel poles, which is sort of obvious from the planarity of this diagram. And so we really have this kind of key simplification here that this is a meromorphic S matrix that for fixed, so U is like a momentum transfer, which in the physical region is negative. And so fixed negative U, we only have poles for the positive real X. There's no pole for negative S. Poles for negative S would be interpreted as T-channel poles, and they would give rise to a physical state of isospin with this absence. Okay, so this is a reason why meson scattering is a bit more constrained than global scattering, because we really just have an amplitude with poles for positive real S. Okay, so in principle, what would be one way to formulate this booster problem is to include among what are the data that I want to boost with the masses of all the mesons and their own shell tree quantities. Of course, that's complicated. And in the case of pions, there is sort of a very useful way to repackage this information, which is to just consider the effective field of pions, integrate out at 3 level the massive mesons, which of course you can do because the other key simplification, of course, large N allows, the pion or the pion meson exchange is suppressed by 1/n. So you can always work at 3 level in this putative theory that has some QCD to a theory of infinitely many mesons with cubic interactions. And so integrating out the massive meson at 3 level, what do we find? Well, of course, we find the effective theory for pions, which is the good old chiral Lagrange. So if I knew the entire set of mesons and their couplings, I could just compute, of course, the higher derivative terms in the chiral Lagrangian. But we will just parameterize them. So we will use as our set the space of data that we will want to carve out, rather than try to carve out the space of masses of mesons in that coupling. We will try to carve out the space of higher derivative couplings in the chiral Lagrange. So this is the restatement of the same, and that here that of course.
Leonardo, but say,
Yes.
for example, just the point that the amplitude, say at S equals 0 and M pi equals 0, it should be 0, for example, that there is no term of 0 order. Is it constraint for you, or how?
So
how
I will comment on that. I will comment on that. The
Okay.
short answer is that in principle it is a constraint. Unfortunately, because we will need to consider subtractive dispersion relation, we will actually not be able to impose that constraint. But I'll come back to this point. So this is of course the infinite power of higher derivative interaction. Of course, the fact that we have this broken, we have the hidden SUN times UN symmetry fixes higher pion scattering in terms of the 2-to-2 scattering. But since today we will just consider 2-to-2 scattering, we do not actually see that. So the nonlinear realization of SUN times SUN will not, SUNF times SUN will not be relevant for us. And so we will just carve out the space of higher derivative interactions. that is more convenient, in fact, to rephrase in terms of on-shell coupling. So the amplitude is completely analytic, and as was just remarked here, if you look, I hope this is NL, right? So the amplitude has this sort of infinite polynomial expansion in S and U because it's analytic, and indeed it starts of order S plus U, right? Because there's no constant term here. You see that N starts from 1. That's indeed the constraint that pions are derivatively decoupled. So you see here that the leading term is S plus U. Then at the for derivative order, there are two invariant, two separate invariant to carry down, which I'm calling G20 and G21. So of course, these can be easily related to L1 and L2 with a little bit of algebra. And the point I want to emphasize, G1, the coupling G10 is just inverts F pi squared, and that goes like 1 over n. And so all do these other terms. All the terms in the effective action are suppressed by 1 over n, which is why we're justified to treat the effective field period at 3 level. So we actually play a rather different game from the one that is usually played when you deal with the chiral Lagrangian. The chiral Lagrangian for final n, what you're supposed to do is to decide what is the precision in energy over the cutoff that you want to go. And once you make that decision, you need to balance the number of 3-level terms that you go up to with loops of terms of lower order, according to some well-understood power counting rules of effective field. But we will not do that because for us, n is the largest number. And so loops are always suppressed. So we are trying to investigate this putative large n theory, which hopefully one day will be understood as a string theory. In this putative large n theory, we just have an infinite number of particles that are weakly coupled. Their interaction goes like 1 over n, and in that theory, we're perfectly justified in anomaly loops. On the other hand, the higher derivative term should be included all the way up to the field. Okay. So what are the so the idea is going back here. We want to carve out the space of this G10, G20, and G21. Okay, so one first observation is that since everything is proportional to 1 over n, really the problem is projective. You can rescale n by any amount. And so the best we can hope to do is to in fact put constraints on ratio, say G20 over G10, G21 over G1. Moreover, since these numbers have different dimensions, we really need a dimensionful quantity in order to get dimensions this number. But that dimensionful quantity is very obvious. It has to be the cutoff of the effective field theory. And what is the cutoff of this effective field, which is the mass of the lightest meson, so it's just the mass of the rock. So the parameter space that I want to carve out will be ratios of these couplings in U, where the mass of the row is 71. And the idea is that not anything goes. A generic choice of these low energy parameters will be in contradiction with the statement that they must come from a healthy S matrix.
Sorry, but why isn't the cutoff 4 pi f? Why would, or is that equivalent to the M row? I think.
You can play various games, but for us, the natural cut, okay. We will work with the mass of the row. We're not doing loops, right? So there's no loop counting parameter.
So that's the land of 4 pi
The,
f. Is
the natural scale where this Lagrangian function.
I see. Yeah.
So if you look at the analytic structure here, so we're expanding the matrix around this point, where everything is analytic. And where will that start making sense? Where the first singularity is the pole that corresponds to it.
Yeah.
In QCD, they're not too different, right?
Yeah, they're not too different in QCD, but just wondering.
But we will play precise mathematical game.
But you
Precise
can still
mathematical
intrigue
game is that we're going to, of course, impose unitarity. Now, again, since we are expanding things to leading greater than 1 over n, so the unitarity imposes that, for example, one consequence that the imaginary part of the amplitude has to be written as a sum with a spectral density. And the spectral density really has to be a two-sided bound from unitarity. However, remember that this spectral density for us also contains a factor of the pion-pion heavy state interaction. So the spectral density is suppressed by 1 over n, which really means that we are never in any danger of saturating the upper bound. So the only condition that we will be able to impose in the 1 over n theory is that the spectral density is positive. So, and then very crucially, we will have to make an assumption about the high energy behavior in the Regge limit. The Regge limit is the limit of small angles, so it's a limit of high energy and fixed momentum transfer. And as is well known, QCD for finite n, the Regge behavior is controlled by the Pomeroy. And so it's a bit better than 2. But we will make an assumption which I believe is very safe, but it is a crucial dynamical assumption we are going to make. That in our meson problem, we will the Pomeroy will be in fact suppressed. So that's clear from a variety of perspectives. In the language of string theory, the Pomeroy is a closed string. And so it comes from a diagram of this kind. And you can also really see this in the data that if you work for fixed n, there is an intermediate region where it's the roll trajectory that controls the energy behavior, and then eventually the Pomeroy sets in. And the statement is that if we take the large n limit first, the Regge behavior will be controlled by the rho, which has limits at 0.5. And so what we'll be using is that the Regge limit of the whole amplitude with flavor factors can be rephrased in the statement that either the zero angle or backward angle, pi angle scattering of this our basic amplitude grows slower than s for large s.
But sorry, but you previously told us that MS goes like S, right? It went like S plus U. I think that's what you had on.
No. So
That's for small s.
So what I told you earlier is that I have an effective field theory
Ah, yeah, MSU goes
that is valid that for small s and u, as any effective field theory, will give, in this case, I just did a 3 level, it will give me an analytic amplitude, which in fact contains arbitrary high powers of s and u. That's the behavior for small s.
small S.
Okay.
Yeah.
And obviously, this expansion will break down. We will have some at best some parameters of convergence. And I'm exploring the behavior for large S, in fact, large S along any range.
But you know what you are saying about vacuum amplitude implies that vacuum amplitude is suppressed like 1 over n, right? Because if you are saying because rho meson exchange, it is like exchange. I would say isospin flip, right? Because rho meson has non-zero isospin, and vacuum amplitude implies that a vacuum amplitude is additionally suppressed by 1 over n.
Yes, correct. That's correct. In fact, it's like automatically clear. If you just look at the large n counting, the vacuum amplitude will have to come from a diagram of this kind, which is suppressed. And so we will make the assumption. This is a crucial assumption, which I think is very safe. It's borne now by the data. Namely, that this mesonic amplitude grows slower than s.
So this is so you can you're going to do contour integration.
Right. So now we are after this preparation. It's sort of clear where we're headed. We're going to write the dispersion relationship for this amplitude, and so ideally we will write the dispersion relation for the amplitude itself, but that cannot be done because the amplitude grows. So the best we can do is the dispersion relation m over s. That means we need one subtraction. But this answers sort of the previous question. If there was a constant in M, that would be washed out by the need to do this subtraction. So the constant, we will be actually be blind to the statement that the pion amplitude starts the constant in the low energy sphere. And so the game is simple. So we write a contour at infinity. And you see, I'm integrating over S prime, where K is an integer that goes 1, 2, etc. So given the assumption I made about the amplitude, the decay slower than S, you see that the contribution from infinity drops out. So I have 0 here. And then we play a familiar trick with the form the contour, and we get two contributions. One from S prime equal to 0. S prime equals to 0 is the regime where the effective field theory expansion makes sense. So from here, I will extract I can use the expansion and effective field theory from the Lagrangian. And then I will set that equal to the contribution from this infinite set of poles, or in principle, we will actually treat this for pragmatic reasons at some continuous spectral density that comes from the high energy. And so the high energy can be massaged in a way that, again, just uses the kinematics of the rotation group. And the only thing that contains dynamical information is the spectral density, of which we know strictly nothing except that it's positive. So you say, okay, what have you accomplished? You are writing some low energy effective field theory coefficient that you don't know, in terms of some high energy spectral density you don't know. So what is this about? Where is the progress? So just as a matter of notation, so you see this pj1 over plus u over m squared. So we are integrating over little m. Little m is the integration parameter that goes from the cutoff all the way to infinity, and we are summing over j. And as a matter of notation, I'm indicating by this bracket, this average meaning integral over little m and sum over spin of a precise function of little m and j, weighted by what? By an unknown spectral density rho j of s. So to be concrete, so remember, I'm integrating over S for fixed U, and I can do this for every choice of integer k. So for each k, I have a whole function of U, which means for each k, if I further Taylor expand in U, I really have an infinite set of some rules that relate the low energy coefficients in terms of some high energy average. That is the logic here. So for example, here, G10 is a term that I can obtain by setting U equal to 0. So G10 is just the average of PJ1, which happens to be 1 over m squared. So G10 is just literally the average over m squared of the unknown spectral density, etc. Why is this useful? Well, this is useful because hidden here, there is in fact a very powerful constraint. The power constraint on the fact that the spectral density has to be positive. And so positivity of the high energy data, in fact, implies that the low energy coefficient must satisfy certain inequalities. That's the idea. And so again, I'm writing this now very concretely for you have some roots of this kind. And you also will notice, perhaps, after a little bit of thinking, you will notice that some parameters appear twice. So there are two seemingly inequivalent ways you can write them in terms of some roots with high energy spectral data. And the origin of that is in writing with dispersion relation, we treated U and S as symmetric. Right, so we fixed U and do a contour integral over S. And that breaks the constant symmetry of the problem. But the fact that secretly the amplitude is constant symmetric comes back to you in this, in the fact that the high energy data in fact are not arbitrary, they must be related in an interesting way. So low energy crossing symmetry imposes some interesting constraints about the high energy stuff. And actually, this is a really simple but relatively new observation that was, I think, first pointed out clearly in these two papers. And I would say, if I had to pinpoint the technical point that was missed in many earlier analysis, this one. That really there is an infinite amount of power that comes from an infinite set of so-called null constraints that follow from low energy costs.
When you say missed, you mean from these 2021?
No, this paper, I'm saying missed before that. Okay, so these are, everything is so elemental that it really could have been done in the 70s. But it wasn't done. And I think the reason it wasn't done is this idea of looking at theory space was not so popular. And then if you start thinking just in terms of carving out theory space, you really want to understand the systematic set of constraints. And it's this kind of constraint that we spoke. And okay, so I'm going to skip the technicalities here, but there are certain inequalities that can be derived with the naked eye. Look at this one, for example. I told you a moment ago that what I really need to consider is ratios of coupling. So let's put the ratio of this one over this one. This is one of the two for derivative couplings over the normalization of the Lagrange solution, so F pi. And I need to put the power of big M here to make it dimensionless. But remember, big M is the point where I start my integral. And then it's then obvious that this has to be more than one. Right, so this is a very elementary constraint that has been known for a long time. But it's also now clear that with more cleverness, and really to do this systematically, you have to put this on a computer. For example, the second for derivative coupling has spin dependent. It's not so clear how to put an upper bound. But then after a little bit of thinking, you realize that the spin dependence using one of the null constraints can be treated something that doesn't have spin. And so by playing with this a bit, you're actually able to derive an upper bound. And then the idea is, well, let's really put this on a computer, and the idea is it becomes a linear programming problem. You want to write down a sum of objects that is positive, so that when I take the average, it stays positive because I'm integrating with a positive measure. And I can add to it an arbitrary amount of these null constraints because null constraints average to 0. And so with some cleverness, I can derive stronger and stronger inequalities by adding more and more null constraints. And this is the kind of thing we really can put on. At any stage of adding more null constraints, you find a rigorous inequality, right? So there's nothing, the numerics here are the numerics of finding stronger and stronger inequalities. But at any stage of the process, the inequality derived is rigorous. And so, lo and behold, this is what we find. Okay, so this is the exclusion plot in the 4 derivative couplings, normalized in units of F pi, so that the N dependence disappears, and in units of the cutoff, which we take to be the rho mass. And little n here is a measure of the number of truncation of this infinite set of null constraints. For n equals 15, I think there are several hundreds of them. And what you observe is that, again, this is inside here is allowed, outside is rigorously excluded. And what you observe, as often is the case in this kind of bootstrap studies, that include more and more of these constraints, it appears that the plot wants to converge to some region which is stable.
Is that smooth there? Is that line is smooth?
So the line is actually not smooth.
There's a kink there.
There is a kink. Thank you. There is a kink. So So two features of this product are remarkable. Feature number one, this is a compact region. Okay, so from first principles, we have found a final region where the higher derivative concept lie.
But say zero coupling is always allowed. I mean, G2
Yeah.
G2 prime equals
Of
zero.
course, that's always allowed. That's this point here. The higher derivative, if you set all the higher derivative to zero, yes, that's all. Just the kinetic term for the pi will be allowed.
Mhm.
So it's a compact region, which is interesting. So this really makes Wilsonian intuition precise. What would Wilsonian intuition tell you? That the non-renormalizable terms must scale like inverse power of the cutoff. I set the cutoff to 1, so that's automatic. And well, with coefficient of order 1, but you could say, well, why is it order 1 and not order 5,000? Well, it's not order 5,000 because you can look at the axis here. It's truly of order 1. So what this thing does is it makes Wilsonian power counting precise, including the order 1 coefficient. Yes.
This is really cool, but I'm also wondering where would the Sakai Sugimoto model lie? That's some funny UV completion of
That's a
QCD.
great question. I don't know.
Is it an interior? Yeah, it could be easy to plot, right? Because we know all of those.
Okay, so
LECs.
of course, what would
That's Susie.
be fantastic?
No, Susie's broken. It's really the chiral Lagrangian at low energies, but just with some values for the low energy constants.
But isn't the gluino play? It's quite light though. The
So-
gluino is a.
Call it a row.
Of course, what would be fantastic to do is to compare with some precise results for the N QCD in the chiral limit. There's no such results. So the best we can do is to compare with the real world, which is not a bad thing. But the real world is all over the place. So these are taken from experimental papers that fit the do chiral perturbation theory to various coupling experiments. Okay, I have to say we did not do a completely comprehensive analysis of this phenomenological literature, which is a little bit outside of my expertise. But you can see that first, there are several groups which are sort of incompatible, quote, everybody a little bit incompatible with one another. And second, the error bars are quite large. So we actually do almost as well as experiment, just from pure thought, just from very general constraints. Our theoretical error bar is not that far from the experimental error bars. And okay, so obviously it's very hard to tell where QCD here is from this plot, also because this is the real world. So in the real world, n is not infinity, the mass of the core is 0, etc. But anyways, we find this as an encouraging sign that at least there is some overlap. We're clearly not far from reality. If anything, this data won't kind of crowd this boundary line. Okay, so one comparison we can do is with this old chestnut of Hegel phenomenology, which is the Skerman model. So the Skerman model, for no particularly good reason, you truncate the effective action to a particular linear combination of the quartic derivative couplings. Of course, that's in principle there are infinite higher terms you are neglecting. And what recommends this particular choice is the fact that this is the only linear combination of four derivative terms has only 2 time derivative, which makes quantization of the model more straightforward. And the kink of the model, of course, it has solitons that correspond to variance. And rather remarkably, the Skerman model lies precisely on the linear. So from what we can tell, the exclusion plot is exactly linear in this region, and then there is a kink and it curves up. So this particular linear combination is a Skerman model. The Skerman model up here will go all the way up here. And what we're saying, actually, no, the Skerman model is only consistent up to here.
So you're dialing E to move along this line.
Yes. So well, if you really want to put in the number, I'm not taking this very seriously, right? You know, the Skerman model has something
But scheme model could be more generic. I mean, not only this possible term, right? In generic, it could be other terms as well, you know, in high derivatives. So, I mean, it is
so
particular choice.
It is in particular, I mean, this is really a for our own amusement. Of course, nobody believes that either this version of the schema model or any other defined version is the actual truth. It's some model. But you know, what is an intrinsic fact is that this particular line, for reasons which are not theoretically very clear to me, exactly agrees with the choice of the choice that it's made, that gives two derivative impact. Okay, now
It could have been excluded, right?
it could have been, but it's just there. So having done this far, of course, there are many games one can play. And a very obvious one is to refine our analysis by giving more knowledge of the real world. And a famous fact is that the first resonance, which is an actual PQ bar state, is the raw. And so what we really should be doing, and we are doing it, I will comment on that in a few slides, is now consider the effective theory where both the pion and the row are treated as light and everything else is treated as heavy. And you should consider the mixed system of pion and row. But for starters, one thing which is easy to do is just include the row as an internal state. So we include the row explicitly in the effective theory by parameterizing its amplitude explicitly. And then, of course, we still have the infinite power of higher mesons, which are now integrated out, and they give some modified coupling G hat. Now, if I start from here and integrate out the row at tree level, I can match the usual tree level matching or effective theory where the G is get rid of the G hat. So now that's the picture here. Now the row is among the light states, and there's a new cutoff here that is M prime. In the real world, M prime can be pushed all the way up to the mass of the F2 meson.
Aren't there some funny degeneracies at large M between like the row and the A prime?
Right, there are, but they're not relevant because they
Don't contribute to the scattering.
do not contribute to pi scatter.
Aha, okay, thank you.
And so the game that we can now play is push this M prime cutoff in units of M row higher and higher. So of course, if M prime is equal to M row is the plot that we had before. And now we find something rather remarkable that as we push M prime higher and higher, the plot shrinks and it appears to shrink precisely to the kernel line. Okay, so the lesson here is that this line appears to correspond to just the row. Now, that cannot be an exact statement because row exchange grows like S in the regime. Spin 1, so grows linearly with spin. And we assume that our regime behavior is strictly better than S. So we will find that there is actually a unphysical amplitude that corresponds to the exchange of the row in the two channels and some junk at extremely high energy that whose only purpose is like to soften the regime. So this is what we are finding here. We are zeroing in an amplitude if that satisfies our assumptions, because it's possible to marginally improve the just row exchange with something that is at extremely high scale that makes the regime difference. So now we can play another funny game, which is to put a bound on the pi row coupling in units of F pi and in units of the row mass. And again, this is the way you should do this coupling. So the blue line is the rigorous exclusion, and the orange line is some extrapolation, which we more or less believe, because we can only work up to some kind of n, but then you do the plot for various little values of little n, and then you extrapolate. So let's say that the orange line is something that more or less we believe. And again, I don't know what to make of this, but QCD would be around here. In fact, this dashed line is some, to me, completely voodoo phenomenological relation that people conjecture long ago, and it has, I don't know what this means, but there is a funny relation which is very well based phenomenologically. Okay, so what does this all mean? So we can explain certain features of our plot in terms of our physical output. For example, this point here just corresponds to a scalar exchange. And as you vary little m from the cutoff, big M, to 0, you are spanning this vertical line. Similarly, this point up here corresponds to an unphysical funny amplitude that you see. The reason it's unphysical is that if I look at the pole in S, this is something that is infinitely high powers of U, as I could explain. So this would be infinitely many spins that all sit at S equal M squared. Anyway, it's this point here. And since everything is convex, as I change this value of big M, this red curve here is inside the plot. And as I told you earlier, this particular line here, which is the Skirmer line, can be understood as some funny UV completion of the row exchange. I can multiply the row exchange in the S channel times this function of U, plus the row exchange in the U channel times this function of U, and M infinity here, you should think of it as a very high mass, which is much bigger than the mass of the row. And in the limit in which M infinity goes to infinity, we just zero in on this line. Now, interestingly, this amplitude is not unitary all the way. It stops being unitary precisely. So the imposition that this funny UV completion of the ROM is unitary tells you where the line should be. Now, we were a little bit confused about this in our original paper because numerically the kink appears to be still a little bit far from the point, which is down here, where the unitarity stops working, for example. But there was a follow-up paper by Riva et al. Where they actually showed that this is just a numerical issue, that with infinite numerical precision, the kink really is the point that corresponds to this particular line, stopping being unitary. We do not have quite a similar understanding of this upper line, but I would say, despite some initial excitement that QCD possibly was sitting at the kink, the statement that we now can explain this line in terms of some UV completion of the row makes me suspect that the particular shape of the exclusion plot is dictated by something like there are two somewhat unphysical amplitudes. We do not quite understand this one fully. I can tell you a bit more later, but we have some spectrum that more or less explains this line, which is also not quite physical. It appears there's some non-analytic behavior in which amplitude dominates or the other that appears to explain the geometry.
So sorry, so what's the conclusion then? What do you think is at the kink?
So the kink is what we can prove is that the kink is the point where this unphysical amplitude stops being unit.
So just have a row there, that's it.
Yes. But of course, this is just the beginning. Okay, so this was a nice warm-up, simple paper we wrote a year ago, and now we can do much higher things, much more complicated things. An obvious thing to do is to include the row as an external state. Now, the story is significantly more involved, as you can imagine, because the row is a massive spin-one state. So the kinematics are harder, but I have powerful collaborators, in particular powerful students. And so we can do it. And so we're actually doing this with John Albert and then the PISA group, Ivan Eriksson and Alessandro Vicky. And we're getting there. We're almost at the point where we can start doing some numerics. Now the condition of unitarity are a lot more involved. You have to impose that these more complicated methods of spectral density is part of semi-definite. But nevertheless, it's doable. And here we will have access actually independently, for example, to the pi-pi-rho coupling and the rho-rho-rho coupling. And this is interesting because there's another surprising phenomenologic successful model that, you know, for no particular good reason, you introduce the rho as a putative vector gauge boson of some hidden local symmetry, and then in that model, the pi-pi-rho coupling and the rho-rho coupling are related. And so now we will be able to find some regular exclusion plot in the space of cubic couplings. And I mean, of course, I don't think that they will come out to be exactly related, but perhaps there could be a sense in which that particular equality saturates the bounds, much like it happened for the schema model. Another byproduct of this analysis we're doing here, which it was still a bit preliminary, so I didn't have a slide on this. The reason that we're able to UV complete the rho exchange is that the rho has precisely spin 1, which is at the boundary of the Regge behavior that we assume. We assume Regge behavior strictly smaller than bigger than 1, and so the rho exchange can be UV completed. But that actually suggests a natural modification. But of course, we know that the F2 is also there. So actually, we force in pi-pi scattering the presence of the spin 2 part. Intuitively, it's going to be much harder to UV complete that, because that goes like S squared. Regge behavior has to be like S. And so what we're actually finding is that the moment we force a spin 2 amplitude, we need a whole infinite Regge trajectory. So forcing a spin 2 amplitude is such that now the bounds will be saturated not by a single spin exchange, but the infinite power of spin, which is precisely the kind of physics you want to start seeing. So this was a bit too crude because we did not assume enough. But the moment you start assuming enough, for example, the fact that you truly have a higher spin particle. The point is that what is higher spin in this part? Higher spin has to be a spin that violates your Regge assumption. And so it has to be greater than the Regge behavior. The moment you start inputting that, then we really start seeing the physics of Regge, which I find exciting. And then another bit of thing I'm going to say a little bit quickly.
I'm sorry, may I ask you, but when you consider, say, triple rho coupling, right? And imagine that it is like, you know, kind of non-abelian rho, right? Then you have certain structure for this coupling, right? And I wonder how it, you know, fits your consideration.
Right. So if you actually look in detail, there are two independent rho-rho couplings that you can write down, and yeah, we are proceeding in a completely general way. So we are writing the most general parameterization.
No, I agree. But this kind of non-abelian structure implies that it is derivative of the field right there, because no, I mean, if you write this coupling, you know,
this particular model would predict that one of the two structures is 0 and the other is
right. It's what I'm asking about.
So yeah, we are, unfortunately, I don't have plots to show you yet, but that's precisely the kind of question we'd like to address. So. If we derive rigorous bounds, how do they compare with this particular model? So of course, everything I've done so far is valid for a larger class of theory in QCD, right? There are many theories that have similar parameters, symmetry breaking, that have massless particles, etc. And so, again, the game here is what assumptions can we make that are reasonable, that would allow us to corner QCD. And obviously, one very robust kind of game that you can play is matching anomalies. And so famously, there is a Toft anomaly in QCD that corresponds to triangle diagonal. You have the axial current with the vector current, either the non-abelian or the abelian part, which you can capture in this anomaly equation. This is the diversion of the axial current, and Q is some charge matrix which is embedded diagonally into U and F. And F is the U1 gauge pulse that corresponds to gauge in that. And so famously, you need the Vesuvino term in order to match anomalies. That's well understood story. Without the Vesuvino term, you don't have, for example, K plus K minus 1 to 3 pions. And then, of course, this seems hard because to read off the Vesuvino coupling, it appears that we would have to do 5 pion scattering, which seems complicated. But there is a well-known trick, which is let's turn on a U1 background gauge field, and then the Vesuvino term will contain, in fact, a term that famously couples the pi 0 to F wedge F. That's a term which is responsible for the Newton pi. So we can actually take a shortcut, and rather than looking at 5 pion scattering, which is complicated, we're now going to scatter photons. Okay, so we will consider a process where we have the system of pions as before, but now we also have external photons. The photons are external in the sense that they're not dynamic. So in other words, this is just a trick to compute form factors of this U1 curve. But the game is very similar. Now, again, we're now going to write this meromorphic as matrix for this larger system. Again, it's very involved, but thanks to my powerful student, here is a preliminary plot.
But in this way,
shown here, yeah.
I'm sorry, but in this way, we consider this amplitude with photon. You can consider also amplitude where instead of photon is a rho meson, right? Because photon could go to rho, and then you have explicitly A1 in resonance region, right? So I wonder about this axial.
I did not understand the last part of your.
No, because when you have pi and gamma. Or instead of gamma, it could be rho. Then in the chain, you have exchange by, say, A1 meson, axial meson. So I wonder.
Oh, yeah. So, I mean, you can do all sorts of more complicated systems. This is a self-contained thing we can do. So this photon is not dynamic. So I'm not going to exchange the photon in the intermediate.
No, right, but A1 is dynamical. Say A1 goes to pi gamma.
So indeed, you have to be careful. I don't particularly remember the A1, but we were careful. So we really did consider. We're just doing the most general kinematic possible thing. So all mesons, which with the correct quantum numbers, will be exchanged.
I see.
And this is going to be captured by the fact that now the spectral density will have different labels that parameterize different quantum numbers, and you really have to consider them all. So we did the most general thing. And here is a very preliminary plot. So this is the same exclusion plot that I had earlier. With the numerics a little bit cruder here, but whatever. You see the kink here more or less. And it's been color-coded with a number that putting the details will take me a while, but you can think of this as a measure of the chiral anomaly suitably normalized. Well, at the beginning, we were a bit naive. We thought we could literally input the value of the UV chiral anomaly, which is equal to the number of colors. That doesn't quite work because you have to consistently normalize the wave functions. And so there are normalization factors that enter here, and the best we can do is to plot the chiral anomaly normalized by an unknown effective theory coupling in the pi gamma system. Nevertheless, this is a thing you can do, and you see there are constraints. So it appears that this particular ratio, the chiral anomaly over this Lagrange coupling, wants to be maximized in the lower part of the diagram. This is all very preliminary. But the general message that now we really get to look at this larger set of parameters that also involve the chiral anomaly and then eventually also the mixed flow system. Okay, so I'm out of time, and so I'll conclude. So we took a new stab at this very old problem. We have exclusion plots which are correct and general. They have intriguing features that make contact with some strange Voodoo QCD. There's a lot more that one can do, and I highlighted some of the possible directions. And then, indeed, the main question really is which assumptions are needed to corner larger QCD, or perhaps some other theory. I mean, of course, I would love to corner QCD, but if it turns out that instead some other theory that you may care about, three-dimensional frequency that you're not can be nailed by this method, that would also be nice. Thank you.
Yeah, some questions.
Yeah, so this, I think I probably asked you this before, but this Hoof model in 2 dimensions.
Yes.
I mean, do you learn any? Because there we know the meson spectrum exactly. So do you learn anything from this?
We haven't tried. So the question is about the top model. The top model, one thing that you could try, and we haven't tried, I think it would be a good problem, is we to input the spectrum and try to bootstrap the packets. So that I think should be a doable thing. You just take the spectrum numerically from the top integral equation and then.
So that's what you mean by the D equals 3? Is that
No, D equals to 3 was. Why
other?
not?
Just
D
other.
equals to
2. Yeah, D equals 2.
You can do
But
equal- you
but
can
in
do
D-
equal to this.
In D equals 3, you would just do what you were just doing.
It would be extremely similar. I don't have any particular reason to think that it would be simpler, but who knows?
I see.
Would putting in, is there any way to put in the absence of heavy states that are or have mass order 1 at large uncounting, but are otherwise heavy compared to the QCD, which are fermions? It's like, for example, that would start excluding things like the Sakai-Sugimoto model, which is a deformation, yeah, which has polynomials.
We're considering a given to the two process.
Yeah. Oh, so right. So at tree level, none of that can contribute.
No,
Anyway.
no,
Uh-huh. That's too bad.
Sakai Sugimoto, it's a great question to know where it is in our student, but I don't know the answer.
Is it kind of easy to include the correction to this Gaussian meaning, like subleading of pounds?
These methods would not quite apply. You have to start considering loops, the effective theory, and the way I phrase it is that my interest in the subject is proportional to that.
Can you comment on the sigma resonance? Because we know experimentally that this spin zero, scattering is relatively large, right? At chi meson, we know that it is 45 degrees for delta. So it's pretty. This spin zero channel is clearly expressed, right? So it means that it goes up very fast. And how it reflects in your.
So I'm certainly not an expert on the phenomenology. My understanding is that there's a consensus now that the sigma resonance is really not a 50-bar pair. It's something like
no, but look, phenomenologically it doesn't matter how you call it. What phenomenologically important that the scattering at this channel J equals 0 is large. It's zero at say 0 point, but it's kind of 45 degrees at mass of 500 MeV. I mean at Kn.
So I would say that that has to be a subleading effect at large. So it's very interesting to know what.
No, because it means that no, but I believe that you are implying that it is kind of next order in 1/n, right? That's why I'm asking.
That's exactly what,
Right,
what
and that's why I'm asking about this, because it's next order in 1/n, but it is, but it's crucial, of crucial importance phenomenologically.
right, but you could say something. Okay, I don't know whether there's any relation, probably not. But the 80 prime is a similar story, right? So a strictly infinite and the prime is massless, but of course we know that really the mass of the prime goes like an F over NC. And so in the real world, the prime is far from massless, and we in the top limit we don't see the eta prime. But of course, so I'm imagining that I don't know if it's the exact same mechanism, but some mechanism like that for this particular phenomenology of the sigma, the top limit is not.
No, but okay, I can formulate my question in a different way, because if you believe that say sigma is like next order in 1/n, then I would wonder whether you can in your approach can follow up 1/n corrections, right?
Yeah, that's a good question. I haven't thought about it. Yes.
I have a quick comment on this discussion that you just had with Arkady, and then a question. So the comment is that I think in the structure of what you said, it would also all be consistent with the different large unlimited QCD that Misha Schiffman, who's sadly traveling, is not here, explored with Adi Armoni and Gabriele Veneziano, which is when you take works in a 2-index representation.
You could try, yes.
And then pretty much everything that you said would just go through. Just the powers of n would be different, but you don't see them anyway because you normalize that away. But the eta prime, the eta prime would be
the Veneziano limit, of course, would also be, I think, more or less.
That's true, but in the Veneziano limit, mesons can decay. So that's a different story. But in the antisymmetric QCD limit, you still have a bunch of poles.
Yeah.
All of that's fine, but the eta prime is heavy.
Yeah.
So that's for whatever that's worth. I don't know whether that's helpful.
No, it's a great.
But glue ball to meson amplitudes are still suppressed, so it wouldn't help with the sigma. But anyway, the question that I had was, do you know whether lattice QCD might help here?
Okay, so lattice QCD does not compute this G2 and G2 prime.
They can I mean, it's not easy to do scattering on the lattice, but they do have methods of doing it using the Lucia method and so on.
One thing, of course, that should have at some level is that in the larger limit should be able to more or less work in the quotient.
Exactly.
Not quite, because of course you still need balance. But you still need to somehow look at pions. So you need you need valence quarks, but not C quark.
Exactly.
So there has.
But that's a technology that they know how to handle.
Yeah. So, by all means, if you know some, if you have any friends.
I do have friends. Yeah, no, I should encourage them to look at this.
If they're willing to compute, that would be wonderful.
But you could also ask the same question in holographic QCD, right? You could
Yes. That's what I was asking earlier with Sakai.
Yeah, holographic QCD.
Oh, no, but not Sakai Sugimoto, just more the ADS.
Oh, right, just like a hard wall kind of thing, and then see
Yeah.
what it says here. That's a great idea.
Yeah.
Right, I mean, you can play those games.
But people probably already did that.
People play those sorts of games with holographic QCD. To be honest, okay, so one can compare all these models to our exclusion. Well, my viewpoint is that, okay, the time for models is over. You either do QCD, which is the real thing, or you do some rigorous exclusions.
Leonardo,
that's the way I would.
Okay.
Leonardo, the question is, can you apply it to stuff like, for example, non-leptonic transition, like K goes to some number of pi, or semi-leptonic transition? Because
can you repeat the non-leptonic such as I missed the word?
Yeah. No, I mean, I wonder about, this, say, non-leptonic transition, like decay of K goes to 3 pi, for example. Instead of scattering amplitude, you can go to non-leptonic decay. Like one of the problems is K goes to 2 pi, and it is, example where lattice was struggling for many years to explain why the amplitude K goes to 2 pi is so large.
Would this be captured by the leading large N? If it's captured by the leading large N, I think so, but
No, but if it could be some kind of hint why this large N approach allows you to explain this enhancement in K goes to 2 pi delta I.
So one comment that I had, of course, everything was done now for massless quarks for simplicity. Of course, we could generalize this to a different. We could, for the kind of question you're answering. I ask, of course, it's important that the kaon and the pions are not treated as part of the same object. So I would have to introduce some flavor break. Which I think one could do, but we haven't done.
Okay, well, if anybody's any other questions, they can find Leonardo for the rest of the day here. And
Thank you very much.
There'll be a dinner, so if you're interested, please talk to me or Tony. Thank you.
So. Excellent.